The next problem asks us to calculate the density of nitrogen gas at 125 degrees C and a pressure of 755 millimeters of mercury. If we had the mass and the volume of the nitrogen gas, we could calculate the density that way, because density is mass over volume. But we don't have the mass and the volume here, but we have a generalized formula where we can calculate the density from the pressure, the molar mass, R, the gas law constant, and the temperature. The molar mass of N2, nitrogen gas, is 28.02 grams per mole, and that's because it is a diatomic molecule consisting of two nitrogens, and nitrogen is 14.007 grams per mole. Well, let's go ahead and get started with this. So first we have to convert all of our quantities into units that match our gas law constant, which is 0.08206 liters atmospheres per mole Kelvin. So we convert temperature to Kelvin. Then we need to convert pressure to atmospheres using our conversion factor. 760 millimeters of mercury is 1 atmosphere. That gives us 0.99342 atmospheres. Now we're ready to use our formula. Density is equal to the pressure times the molar mass divided by R times the temperature. If we plug everything in, our pressure, our molar mass, our R, and our temperature, we find that the density of nitrogen gas is 0.852 grams per liter. As we would expect, our units are in mass over volume, and gases are normally expressed in grams per liter. Now let's work the for practice and the for more practice problems. Alright, so for practice 6.7, calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees C. Again, our formula is density equals pressure times molar mass divided by R times the temperature. We need to convert pressure to atmospheres and C to Kelvin. All right, so R, as we've used it before, is 0.08206 liters atmospheres per mole Kelvin. Okay? All right, so the pressure in atmospheres is equal to 742 millimeters of mercury, and 1 atmosphere is 760 millimeters of mercury. So that gives us 0.97631 atmospheres. All right. Next, our temperature in Kelvin is equal to our temperature in degrees C plus 273, which is equal to 318 Kelvin. Now we're ready to plug into our formula. Density is equal to pressure times molar mass divided by R times the temperature, which is 0.976316 atmospheres times 131.293 grams per mole divided by 0.08206 liters atmospheres per mole Kelvin times 318 Kelvin, which is equal to 4.91 grams per liter. And the units make sense, so we can assume that we got the right atmosphere, that we got the right answer. Okay? Before we move on, let's do a unit analysis. Okay? Atmospheres cancels here. Moles cancels here. All right? Kelvin cancels here, and we're left with grams per liter. All right, next let's work the for more practice problem. The density of a gas is 1.43 grams per liter at a temperature of 23 degrees C and a pressure of 0.789 atmospheres. Calculate the molar mass of the gas. Our temperature in Kelvin is equal to 23 degrees C plus 273, which is equal to 296 Kelvin. Our pressure is equal to 0.789 atmospheres. All right. The density is equal to the pressure times the molar mass divided by R times the temperature. Okay? And so we're asked here to calculate the molar mass of the gas. So we need to solve for molar mass. How do we do that? We multiply by both sides of the equation by RT and divide both sides of the equation by P. And therefore, we see that molar mass is equal to density times RT over P. Now we can plug in. Our density is given, which is 1.43 grams per liter. Our R is 0.08206 liters, atmospheres per mole Kelvin. And the temperature is 296 K. And let's divide by the pressure, which is 0.789 atmospheres. Our answer turns out to be 44.0 grams per mole. Just to check, let's do a unit analysis, okay? Liters cancels here. Atmospheres cancels here. Kelvin cancels here. And we're left with grams per mole.